Chapter 7 is titled Rotational Motion in the Law of Gravity. It starts off with angular speed and angular acceleration, then it is rotational motion under constant angular acceleration, relations between angular and linear quantities, centripetal acceleration, Newtonian gravitation, and finally, Kepler's laws. Chapter 7 starts with angular speed and angular acceleration, and there are a few equations that you must know. The first one is theta equals s over r, where s is arc length and r is radius. Then you must know average angular velocity, omega equals change in theta over change in time. Finally, average angular acceleration, alpha equals change in omega over change in time. Another very important thing to know is how to convert revolutions to radians and radians to revolutions. To convert radians to revolutions, divide by 2 pi, and to convert revolutions to radians, multiply by 2 pi. These equations would be useful if you want to find something like the angular displacement of a helicopter's rotor blades, or even the angular speed of a bike as you pedal. Now let's do a practice problem. A potter's wheel moves uniformly from rest to an angular speed of 1 revolution per second in 30 seconds. Find its angular acceleration in radians per second squared. To solve this problem, you must use the equation alpha equals change in omega over change in time, and plug in 1 revolution per second for omega and 30 seconds for change in time. Then you must solve and multiply by 2 pi to convert it into radians per second squared. The second part of Chapter 7 is titled Rotational Motion under Constant Angular Acceleration, and these equations mirror those of the linear motion equations. Just substitute the variables used for angular acceleration and angular problems in for those of the linear motion ones. These equations can be quite useful if you want to find something like the angular displacement of a windmill as it is hit by a gust of wind. A problem in this section would most likely be like this. A centrifuge in a medical laboratory rotates at an angular speed of 3,600 revolutions per minute. When switched off, it rotates through 50 revolutions before coming to a rest. Find the constant angular acceleration of the centrifuge. To solve this problem, all you have to do is convert revolutions into radians, and then plug it into the equation alpha equals omega squared minus omega initial squared over 2 times the displacement theta. The third section in Chapter 7 is titled Relations between Angular and Linear Quantities, and the only equations you must know are tangential speed, vt equals r times omega, and tangential acceleration, at equals r times alpha. The fourth part of Chapter 7 is titled Centripetal Acceleration, and the only equation you need to know is v squared divided by r. There are various other versions of this equation. I put them below. Centripetal acceleration plays a major role in daily life, especially when you're on a Ferris wheel or driving your car and you need to turn. Let's do a practice problem. An air puck of mass 0.25 kilograms is attached to a table using a string and allowed to rotate in a circle with the radius of 1 meter. The other half of the string goes through a hole in the middle of the table and is attached to a mass of 1 kilogram. Can you find the tension of the string and the speed of the puck? To solve this problem, you set the forces of y equal to the acceleration in y, except there is no acceleration in y. So you end with t minus mg equals 0. Then you just plug and solve. You'll end up with 9.8. To solve for the second part of this problem, you need to set the tension equal to the centripetal force because everything is in equilibrium. Then you plug everything you know in and solve. Part 5 of Chapter 7 is all about Newtonian gravitation, and the only equation you need to know for this one is Fg equals cap g times m1 times m2 divided by r squared, and that'll give you the force of gravity. Here's a clip showing gravity at work. Here's another practice problem. The average distance separating the Earth and the Moon is 384,000 kilometers. Find the net gravitational force exerted by the Earth and the Moon on a 3 times 10 to the 4th kilogram spaceship located halfway between them. To solve this problem, we use the equation Fg equals cap g times m1 times m2 divided by r squared. Then plug in half of the distance between the Earth and the Moon for the r, the Earth's weight, and the spaceship's weight. This will give us the gravitational force exerted on the spaceship by the Earth. Then we do the same thing for the Moon, plugging in the same radius but changing the mass of the Moon, and then solving for the force of gravity. After solving both equations, we get the force of gravity Earth exerts on the spaceship as 325 newtons, and the force of gravity the Moon exerts as 4 newtons. Subtracting one from the other, we get 321 newtons of force. The sixth and final section of Chapter 7 is all about Kepler's laws. His first law is any object bounded by a force that varies as 1 divided by r squared will move in an elliptical fashion. Here is a cool animation of this in motion. Kepler's second law is that two areas swept out along the path a planet takes while it goes around the sun are equal if they are of equal time intervals. Kepler's third law is the period of a planet squared divided by its distance from the sun is the same for every single planet. Here's an animation of the planets in our solar system and their relative sizes.